Hi class, this is Miss V, your chemistry teacher. In today's video, we are going to talk about chemical bonds. Not the type of bond, but this type of bond. The chemical bond is the force of attraction that holds two atoms together in a molecule or an ion pair. The bonds are formed either by transferring or sharing of electrons to achieve a stable configuration similar to the noble gases in the periodic table. The noble gases, with the exception of helium, have 8 valence electrons, responsible for their stability and inertness. Hence, this became the foundation of the octet rule, which states that atoms other than hydrogen tend to form bonds until surrounded by 8 valence electrons. So for octet rule, elements tend to bond in such a way that each atom has 8 electrons in its valence shell, giving it the same electron configuration as a noble gas. So literally every element tends to bond to each other, unlike the noble gases. In demonstrating the bond formation, Gilbert Newton-Lewis dot symbol or Lewis dot structure is used. The Lewis dot symbol consists of the symbol of the element and a dot equal to the number of its valence electrons, as shown below. So here are the elements and the dot that represents the number of electrons or valence electrons present on that element. So how do we know the number of valence electron of an element? By simply looking at the group number of the element at the periodic table. The group number represents the number of valence electron in an element. Let's have an example. Lithium is from group 1A, alkali metal, and the number of valence electrons present is 1. So from group 1A, that is why it has 1 valence electron. And the Lewis dot structure of lithium is like this. It only has 1 dot. So why it only has 1 dot? It's because again, it only has 1 valence electron. And to prove why it only has 1 valence electron, let's look at the electron configuration of lithium. We all know that lithium has an atomic number of 3. Atomic number is 3, meaning lithium has 3 electrons. So by using this, by doing this electron configuration, we have here the electron configuration of lithium, 1s2, 2p1. If we look at the distribution of electrons on the main energy level as seen below, as you can see, the first main energy level, based from our electron configuration, it holds 2 electrons. So our first main energy level has 2 electrons on it. While our second main energy level has only 1 electron, since there are only 3 electrons in our lithium. So that is why the main energy level or the second main energy level only has 1 electron. And the second main energy level is the outermost layer or the outermost valence shell, the main energy level, wherein we find that it only has 1 electron. So that 1 electron is our valence electron, the electron in the outermost layer or the outermost valence shell. Another example is boron. So boron is from group 3A, so meaning to say it has 3 valence electron. And the Lewis dot structure is like this. So why 3 dots? Because it has 3 valence electrons at the outermost shell or the main energy level. So that is why it has only 3 dots or the 3 valence electron. Now if we look at the electron configuration of boron, boron has 5 electrons because the atomic number is 5, so meaning it has 5 electrons. And the electron configuration of boron is 1s2, 2s2, and 2p1. So for a total 5. If we look at the distribution of electrons on the main energy level, as you can see, the first main energy level can only hold the maximum number of electrons of 2. So on the first main energy level, it only has 2 electrons. And on the second main energy level, the 2s2 and the 2p1 combined, so 2 plus 1 is equals to 3 electrons. That is why the second main energy level only has 3 electrons on its outermost layer. Another example is neon. So we all know that neon is a noble gas. They are known to be stable. So noble gases are stable because it belongs to group 8A, which is the noble gases, and it only means that it has 8 valence electrons. So if you look at the Lewis dot structure or symbol, neon is surrounded by 8 electrons. So the 8 dots that we see on the illustration is the Lewis dot structure of neon. So it has 8 dots, represents the 8 electrons or 8 valence electrons. So if we look at the electron configuration, we all know that neon has 10 electrons. And if we do the electron configuration, it is like this: 1s2, 2s2, 2p6. And if we look at the distribution of electrons per main energy level, for the first main energy level, the maximum number of electrons that it can hold is 2 electrons. So on our first main energy level, we have 2 electrons. For our second main energy level, it is known that it can hold up to 8 electrons. And for our case here, our neon's second main energy level has 8 electrons as well. So the outermost valence shell is full, so it reached the maximum number of electrons. That is why it is complete. That is also why it is stable. Now let's move on to the types of chemical bonds. There are 3 types of chemical bonds. We have ionic bond, covalent bond, and metallic bond. Ionic bond is formed between metal and nonmetal elements. Metals have a greater tendency to lose electrons, while nonmetals have a greater tendency to accept electrons. When a metal loses electrons, it becomes positively charged cation, while a nonmetal becomes a negatively charged anion when it accepts electrons. Hence, it can be said that ionic bonds involve the attraction between 2 charged ions. This bond holds the ions together in an ionic compound. Let's have an example. Let's say we have here sodium and chlorine. Sodium belongs to group 1A. It means that it has 1 valence electron, while chlorine belongs to group 7A. So it means that it has 7 valence electron. So in forming an ionic bond, sodium donates 1 electron to chlorine. Having lost 1 electron, sodium becomes a cation, while chlorine, having accepted 1 electron, becomes an anion. So these positively or oppositely charged ions attracts each other, forming an ionic bond. Another example is a bond between magnesium and fluorine. Magnesium belongs to group 2A, which means it has 2 valence electrons, whereas fluorine belongs to group 7A. It means it has 7 valence electrons. When bonding occurs between magnesium and fluorine, the electrons in magnesium are transferred to the 2 fluorine atoms. Magnesium loses 2 electrons, while each fluorine gains only 1 electron. So as you can see, fluorine has already 7 valence electrons. It has already 7 electrons, meaning it only needs another one election for it to become stable. That is why another fluorine was added, making it 2 fluorines. So they both gain electrons coming from the magnesium. The 2 fluorine atoms gain 1 electron each from the magnesium atom. Having lost 2 electrons, the magnesium becomes a cation, while the fluorine that accepted 1 electron from the magnesium becomes an ion. So it formed ions, the magnesium ions and the fluorine ions. Again, because of the ions present, of course, opposite attracts to each other. We have a negative ion and a positive ion forming this what we call the ionic bond. So this formation of ionic bond forms the ionic compound magnesium fluoride. Another example we have here is a bond between aluminum atom and an oxygen atom. So the aluminum atom has 3 valence electrons because it's under the group 3A, while oxygen came from the group 6A. So oxygen has 6 valence electrons. So to bring the aluminum and the oxygen atoms in correct ratio to form a stable configuration, 2 aluminum atoms and 3 oxygen atoms are needed. So when the electrons of aluminum are lost, positive ions are formed and it attains the configuration of neon. On the other hand, when oxygen accepts the electrons from aluminum, the negative ions are formed. Oxygen also attains the configuration of neon. So the attraction between the positively charged aluminum and the negatively charged oxygen leads to the formation of aluminum oxide. So as you can see on the illustration, the formation of ionic bond in the aluminum oxide between aluminum and oxygen. As you can see, we have here 2 aluminum atom, and each aluminum atom has 3 valence electron. Well, on the oxygen part, we have here 3 oxygen atoms as shown in the illustration. Each oxygen atom has 6 valence electrons. If you count the dots, it's 6 each oxygen atom. So as you can see, when the first aluminum transferred 2 of its electron to one of the oxygen atom, of course, the electrons it gained from aluminum makes the oxygen attains a configuration of neon. If we try to count it with the electrons that was gained from aluminum, it would be 8. So it will have 8 electrons because again oxygen gained 2 electrons from aluminum. So that is why it becomes stable. Okay, so the aluminum still has another 1 electron. And on the bottom part, the same thing happened to the first part, where in the aluminum, another aluminum gave its 2 electrons to another oxygen, making it stable, and it has another electron, or there remained another electron, 1 electron. So that electron from that aluminum and another electron from the other aluminum will be transferred to the oxygen at the middle part. So the remaining electrons from the aluminum, the 2 aluminum, was given to the oxygen, the third oxygen here on the middle. Because of that, it will be stable because again, 2 electrons was given to the oxygen, making it have a configuration of neon. So if you count the electrons present, it's 8. Again, so 2, 4, 6, 8. When we write the election dot or the resulting election dot formula from the ionic bond between the aluminum and the oxygen atoms, it will be like this. As you can see, it is written like this. It has 2. This number 2 represents the number of the element used. We have 2 aluminums that we use. We use 2 aluminums. So it was written to indicate that we have 2 aluminums in this bond. And of course, it is raised to positive 3. This positive 3 again is the valence electron of the aluminum. So it has 3 valence electron and it lost 3 electrons. So of course, it will be positive 3. Now the oxygen enclosed in this parenthesis, before the parenthesis, there was number 3. So 3 here represents that we used or we have there 3 oxygen atoms. Okay, so we have there 3 oxygen atoms, and then it was raised to negative 2. The negative 2 here represents the number of electrons that it can gain. Okay, so negative 2 is the number of electrons that it can gain. So that is the election dot formula for the bond, ionic bond in aluminum oxide. In writing the formula of ionic compounds, the crisscross method is used. The subscript of the cation is numerically equal to the charge on the anion, and the subscript of the anion is numerically equal to the charge of the cation. If the subscript is 1, it is not written. If the charges are numerically equal, there is no need to crisscross since the sum of the valences is 0. The compound is electrically neutral. Let's have an example. We have here aluminum oxide. We have the aluminum ion and the oxygen ion. For aluminum ion, the charge is positive 3, while the oxygen ion has a charge of negative 2. Now, this positive 3 for aluminum represents the number of valence electron or the number of electrons present on its valence shell or the last main energy level. Well, the negative 2 on the oxygen, the charge on the oxygen, which is negative 2, represents the number of electrons that it can gain. The number of electrons that it can accommodate in order for it to become stable. Now, as I have said a while ago, in writing the formula of ionic compounds, we use the crisscross method. Now, the charges of our ions using the crisscross method will be switched from both elements. Like for our case here, the charge from aluminum became the subscript for oxygen, while the charge from oxygen became the subscript of the aluminum. That is why it became like this: aluminum with subscript 2 and then oxygen with subscript 3. So this subscript also represents something. If you can analyze, if we can go back to the formation of the ionic bond of the aluminum oxide, if you could still remember, we have there 2 aluminum, and the subscript kind of represent that there are 2 aluminums, and for oxygen there are 3 oxygen for this ionic bond. Another example of ionic compound is magnesium fluoride. So, magnesium has a positive 2 charge, while the fluorine has a negative 1 charge. Now, these are ions. Okay, so magnesium ion and the fluorine ion. Now, using the crisscross method, those charges will switch. It will become the subscript of one another. So for magnesium, the positive 2 become the subscript of the fluorine, while the fluorine, the charge, the negative 1 charge, became the subscript of magnesium. As I have said a while ago in writing the formula of ionic compounds, if the subscript is 1, it is not written. So the formula here, as you can see, is only magnesium without subscript, a symbol of magnesium, plus the symbol of fluorine with a subscript 2. So that is the formula for magnesium fluoride. Again, 1 is not written. Next is sodium chloride. So we have here sodium ions and chlorine ions. Sodium has a positive 1 charge and chlorine ion has a negative 1 charge. Using the crisscross method, as you can see, the supposed subscript was not written. Again, the first reason for that is both charges are numerically equal. So, as you can see, sodium has positive 1, chlorine has negative 1. They are numerically equal. So, if we add the two, the sum is 0. And another reason is that 1, again, as a subscript, is not written. So, in the formulas for ionic compound, number 1 is not written. So that is why the formula for sodium chloride is only the symbols of the elements. So sodium chloride, the sodium symbol and the chlorine symbol, NaCl. Another example we have here is aluminum nitride. We have here the aluminum ion and the nitrogen ion. So for the aluminum, again, the positive 3 here is the number of electrons of its valence, and then the nitrogen with a negative 3 charge represents the electrons that it can gain from a cation, and for our case, aluminum here will give its electron to nitrogen, forming the ionic compound aluminum nitride. As you can see, they are numerically equal in charge. So positive 3 plus negative 3 will result to a sum of 0. So that is why, meaning to say it will be cancelled out, it will not be written as subscripts. So the formula for aluminum nitride is simply the symbols of aluminum and nitride together. Now let's move on to covalent bond. A covalent bond is formed by electron sharing between the atoms of nonmetals. Through sharing, atoms achieve stable configurations similar to the noble gases. The compound that consists of atoms bonded together by shared electrons is called a molecular compound. Examples of molecular compounds are the diatomic gases and the binary acids. The Lewis structure is used to represent the shared electrons in a molecular compound. Diatomic gases are made up of atoms of the same elements. The Earth's atmosphere is mainly composed of diatomic gases such as fluorine, oxygen, nitrogen. So fluorine 2, oxygen 2, nitrogen 2. To achieve a stable configuration, diatomic gases form bonds that satisfy the octet rule. So for example, fluorine, since fluorine needs only 1 electron to achieve a noble gas configuration, fluorine, if you can still remember, has a 7 valence election. So it only needs one election for it to become an 8 valence election, for it to become stable. So when fluorine bonds with another fluorine, so they will share one of each of their electrons, the octet of electrons is completed by means of electron sharing. Another example is oxygen. The oxygen gas, each atom of oxygen must share 2 electrons because the valence electron for oxygen is 6, meaning to say it needs 2 more electrons for it to become stable. So if we bond 2 oxygens, they must share 2 electrons. Well, each atom of nitrogen, for nitrogen gas, let's say we have 2 nitrogen gases which are bonded together through covalent bond. So the nitrogen gas must share 3 electrons in order to acquire a noble gas configuration, respectively. So as you can see in the illustration below, this is how you illustrate the Lewis structure for this diatomic gases. So we have there the fluorine bonded to another fluorine, oxygen bonded to another oxygen, nitrogen bonded to another nitrogen. In counting the number of electrons, the bonded electrons together with the lone pairs are considered to be part of the atoms involved in that bond. If you can see this illustration, we have here oxygen bonded to another oxygen, forming a double bond. So it formed a double bond because both shared 2 electrons. So if we count this, as you can see on the first circle, we have there 2, 4, 6, 8, because the 8 electrons, so it is stable. Then another oxygen, again, if we count it based on the circle, so we have here 2, 4, 6, 8. So again, it is stable. It achieved the octet rule, or the octet of electrons achieved the noble gas configuration. Next is binary acids. Hydrogen, a nonmetal element, only requires 1 electron to attain a stable configuration. Unlike other elements which follow the octet rule to achieve stability, hydrogen follows the rule of 2. It only requires to bond with another single atom for it to be stable. Hence, one way to attain this is to share electron with halogens to form binary acids. Here's an example of binary acids. So we have here hydrogen bonded to fluorine. Hydrogen shared its electron to fluorine, forming this compound which we call hydrofluoric acid. Another, hydrogen and chlorine bonded together, forming what we call hydrochloric acid. Another one, we have here hydrogen and bromine, forming a bond, a covalent bond, and the compound is known as hydrobromic acid. Aside from diatomic gases and binary acids, here are some of the examples of molecules or compounds formed by electron sharing. Covalent bonds can be single bond, double bond, or triple bond. A single covalent bond is a bond in which 2 atoms share 1 pair of electrons. A double covalent bond is formed when 2 atoms share 2 pairs of electrons, while a triple covalent bond exists when 2 atoms share 3 pairs of electrons. The valence electrons of an atom are not all shared in the formation of covalent bonds. For example, the fluorine gas only shares 1 valence electron, and this electron is called the bonding electron. So the electron pairs that are not involved in electron sharing are called lone pairs or non-bonding electrons. Electron sharing in covalent bonds may be equal or not between two atoms, and these situations resulted into two kinds of covalent bonds, namely polar covalent bond and a nonpolar covalent bond. For nonpolar covalent bond, the electrons are equally shared between atoms. This means their electronegativities are almost the same, and the examples are the diatomic gases. For polar covalent bond, the electrons are shared unequally, resulting in one atom being partially negative and the other being partially positive. An example of these are the binary acids and water. Now let's move on to metallic bond. Metallic bond are bond found in metals. So it holds metal atoms together very strongly. Scientists believe that all the metal atoms, rather than being associated with particular atoms, share the outermost electrons in each metal atom equally. These free electrons can then conduct heat and electricity throughout the metal, and the metal atoms are therefore held together by the electrical interaction between positively charged protons and the negatively charged electrons. Metals do not therefore form compounds with other metals. They form alloys, solutions of one metal in another that seldom have definite formulas or structure.